So good morning to all of you. Today we are going to cover a very important topic in digital system design, that is flip-flop and its conversion. In this PPT, I am going to cover about what are latches, what are different types of flip-flops and their conversion. Starting from the very first topic, that is latches and flip-flops. The very basic difference between latches and flip-flops are that these are both bistable circuits, but latches are unclocked whereas flip-flops are clocked. What is meant by clocked or unclocked? We know that a clock pulse is a level of 1 or 0. If any circuit is triggered on rising or falling edge, then it is called as edge triggered, and if any circuit is triggered on 1 or 0, then it is called as level triggered. So we can say that latches are unclocked, or we can say that latches are level triggered, whereas flip-flops are edge triggered, either using NAND or NOR circuits. So starting from the very first, that is NOR based SR latch. It's a cross-coupled circuit consisting of two NOR gates and two inputs. One is set and other is reset. The final output of latches or flip-flops are complemented. That is, one output is Q, then the other is Q bar. In symbolic form, we can write it as SR, a rectangular block with output Q and Q bar. And in between, we write it as SR. Now, if we start with the working of SR latch, if we set these two values 0, 0, and if the previous state is 0, then it comes to the feedback circuit, that is 0. And 0 plus 0, NOR gate, 0 plus 0 gives output 1. Then this 1 goes to the feedback path, and again 0, 0, then it output becomes 1. Again this 1 goes to the feedback path, 1 plus 0, the output becomes 0, and this 0 goes to the feedback path, 0 plus 0, that is output becomes 1. 0, 0, this value again becomes 0, and this becomes 1. So for 0, 0, the output of this latch will be, if we give it 0, then the next state will be 0, and if we give the previous state 1, then next state will also be 1, that is 0, 0 and 1, 1 means no change. For 0 and 1, that is, if we take set as 1 and R as 0, then if we use the same logic, we check that for any of the previous inputs, the next state will be 0 for R equal to 1. And for S equal to 1, the next state will be 1, which is called as set and reset. These 1-1 combination are not used, means if we take both the inputs as 1-1, then for next output, both outputs either will be 0 or 1, both will be 1, which is not feasible. Hence, it is indeterminate combination. The truth table will be set. S is called as set, R is called as reset, Qn plus 1, that is next state output, Qn plus 1 bar, and state. For 0, 0, there is no change, that is Qn plus 1 equal to Qn. If reset equal to 1, next state will be 0, that is reset. If set equal to 1, next state will be 1, that is set. And for 1, 1, it is undefined or indeterminate state. The same latch can also be designed using NAND gate. We can convert it by replacing S by S bar and R by R bar. So the equivalent NAND based latch has this type of circuit with cross coupled final output. If we talk about the truth table of this latch, again we consider by S bar and R by R bar. So for 0, 0, output is indeterminate. For 1 1 there is no change. If S bar is 1, the output is reset, and if R bar is 1, then output is set. Just the reverse operation of S and R in NOR latch. In place of S there is S bar, and in place of R there is R bar. So if we talk about the timing diagram and we consider SR waveform, then when both the inputs are 0, output is 1. Now when reset is 1, output becomes 0. And again when both the inputs are 0, output remains same state. Then if set is 1, output becomes 1. And when both the inputs are 0, it continues to be in the same state. And this continues. Once the reset is 1, output becomes 0, then same state, and this continues. Now, when we talk about the gated SR latch, as we have seen that previous working is the 1-bit memory cell. If we have to make it an entire latch or entire flip-flop, we have to give it a clock or enable signal, which is called as gated circuit. So for gated SR latch operation, we use one NAND based 1-bit memory cell and 2 external NAND gates to provide the input to this cell. So this S bar, R bar, again S bar is connected to external S and R bar is connected to R, and these 2 flip-flops, one control signal, that is enable. So once the enable signal is 0, this flip-flop is off, so there is no change in the output. And when the enable signal is 1, the same truth table follows, that for 0 0 there is no change. For reset 1, output is 0. For set 1, output is 1, and for 1 1, this is the function table or truth table of this SR latch. If we elaborate this truth table, then we can form the characteristic table by considering all the possible combinations of S, R, previous state, and based on that next state. So when the enable is 1, for SR 0 0, if previous state is 0, next state is 0. If previous is 1, next is 1. For SR 0 1, if previous 0, next 0, and for previous 1 also, next is 0 because reset. For SR 1 0, previous state may be 0 1, next state will be 1. And for 1 1, previous state may be 0 or 1, but next state will be indeterminate, that is don't care. So this is called as characteristic table, and we can solve this table to find out the characteristic equation of SR latch. It uses 3 inputs S, R and Qn. So we prepare a K-map using SR and Qn. The output is 1 for 0 0 1, then 1 for 1 0, 0 and 1 0 1, that is 1 0 0 and 1 0 1. And there are 2 don't care conditions for 1 1 0 and 1 1 1. 1 1 0 and 1 1 1. A quad and a pair, and the resultant equation will be S plus, for this, Qn into R bar. So the output characteristic equation of this flip-flop is S plus R bar into Qn, and this is the symbol of this SR latch. We have derived using 1-bit memory cell NAND latch the complete gated SR latch circuit. This is the truth table or function table. This one is called as characteristic table, then characteristic equation and symbol. Moving towards gated D latch. If we connect a NOT gate between the 2 inputs of SR latch, that is connect S with D, use a NOT gate and connect it to R, then it becomes D latch. So there is only single input D, enable Q and Q bar. As there is a NOT gate in between and S and R, so 0, 0 and 1, 1 combinations are obsolete. So once D equal to 0, that is S0 and R1, output is reset, that is Q equal to 0. And when D equal to 1, S equal to 1, R equal to 0, that is output is set, so Q equal to 1. So what you will give as input D, same is reflected in the output irrespective of previous state. Enable D, Qn and Qn plus 1. If D is 0, output is 0. If D is 1, output is 1 irrespective of previous state. So don't care. We can again solve the K-map of these two terms, enable D and Qn, to find out the equation which comes out to be enable into D plus enable bar into Qn. So this is the characteristic table, characteristic equation, truth table, and the symbol of, this is the symbol of SR latch, S bar R bar, D latch. Then now moving towards flip-flop. For flip-flop, instead of enable, we use clock signal, that is edge trigger. I have already described that is rising edge or called as positive edge. And if there is a clock from 1 to 0, then that is called as falling edge or negative edge, which is represented by a clock with a knot. So if a flip-flop is triggered on level, then it is level triggered for con 1. For positive triggered, symbol is upward arrow, and for negative edge triggered, symbol is downward arrow. So now we move towards clocked SR flip-flop. Instead of latch, if we use the terminology flip-flop, everything remains the same, only the enable represented by clock pulse. And if the clock pulse is positive, then we use this symbol. And if we use negative clock pulse, then we use a notch at the input of clock symbol. All other things remain the same, that is we use again NAND S bar R bar 1-bit memory cell, 2 NAND gate to provide 2 inputs. For same working for 0, 0, there is no change, that is previous state becomes next state. When reset is 1, output becomes 0. If set is 1, output is 1, and for 1, 1, output is indeterminate. So the working is remains exactly same. The only difference is based on the clock pulse. It can be level triggered, that is work on 1, edge triggered, that is work on rising edge or falling edge. If there is a rising edge, then we use this symbol of clock pulse, and for falling edge, we use this symbol for clock pulse. Now we move towards another flip-flop, that is JK flip-flop. In SR flip-flop, we see that 1-1 combination is not used. So to solve this problem, we use JK flip-flop, where in same SR flip-flop, the output, final output is fed back to the input, and S is replaced by J. We can prepare this circuit either using SR NOR based latch or NAND based latch, both are true. So if we do the working of this flip-flop, for each other combination, output is same. We just replace S by J and R by K. So for 0, 0, if previous state is 0, next is 0. If previous state is 1, next is 1, that is there is no change. If reset is 1, output is 0. If previous state is 1, if set is 1, then for irrespective of previous state, next state is 1. And for 1, 1, instead of indeterminate, we find out the output is toggled. That is, if we previous output is 0, next is 1, and if previous one, next is 0. So clock JK flip-flop solve the problem of indeterminate at input 1, 1, and the final output will be toggled. If we solve this K map, then the characteristic equation find out to be J into Qn bar plus K bar into Qn. And this one is the symbol of this JK flip-flop. But there is a problem with this flip-flop. We will discuss this later on. Before that, I will cover one more flip-flop which is derived from JK, that is T flip-flop. If we short circuit both the inputs of JK flip-flop, then it becomes T flip-flop. So if we connect J with T and K both, then it becomes T flip-flop. Using this, only 0, 0 or 1, 1 inputs are considered. So if T is 0, then both J and K are 0, and for 0, 0 there is no change. So for T 0, if previous state is 0, next 0, and if previous 1, next is 1. For T equal to 1, both J and K are 1. For 1, 1 there is toggle. So for T equal to 1 is previous 0, next 1, and if previous 1, next is 0. So that's why it is called as T toggle flip-flop. The output will be toggled. That is reversed form of input. We can make this truth table in a smaller form, T and Qn plus 1, for 0 same, and for 1 inverted. And also we can solve this K map in terms of Qn and T. Then the combined equation will be T into Qn bar plus Qn T bar into Qn. This one is the characteristic equation, characteristic table, as well as truth table. So we have clearly seen that there are 4 types of flip-flops exist: SR, D, T, and JK. Now moving towards the characteristic table of these flip-flops. For JK flip-flop, for 0, 0 there is no change, K equal to 1 reset, J equal to 1 set, 1, 1 complement, that is toggle. For D flip-flop, when D equal to 0, output 0, for D equal to 1, output is 1. For toggle flip-flop, for T equal to 0, no change, for T equal to 1, complement, that is toggle form. So we can clearly describe the excitation table, that is truth table gives output next state based on input, whereas excitation table gives input based on present state and next state. For example, if we talk about JK flip-flop and use its characteristic table, we write all the combination of present state and next state, that is 0, 0, 0, 1, 1, 0, 1, 1. What are the possible input combinations of JK for which output is no change with respect to input? So for input 0, 0, previous state 0, next state 0, so one combination is 0, 0. Again there is one more combination 0, 0 on 0, 1. So we write 0 cross. Now we check for 0 to 1, previous state 0 and next state 1, which comes for JK 1, 0 and 1, 1. So we write 1 cross. Similarly, for 1 to 0, the possible combinations are 0, 1 and 1, 1, that is 0 cross. Sorry, 0, 1 and 1, 1, that is cross 1. And last, for 1 to 1, all the possible combinations are 0 0 and 1 0, that is cross 0. So excitation table means based on present state and next state, we write all the possible combinations of input for that particular. So if we write the same for SR flip-flop using its characteristic table, for SR flip-flop the characteristic table is we write all the input combinations, and for this we write the output. For 0 0, if previous state is 0, next state is 0, and for if previous state is 1, next state is 1. For 0 1, next state 0, for 0 1, next state 0. For 1 0, next state is 1, next state is 1, and for 1 1, don't care. Now using this combination, if we write previous state 0 and next 0, then the output will SR will be 0 0 and 0 1, that is 0 cross. For previous state 0 and next state 1, SR will be 1 0. For previous state 1 and next state 0, SR will be 0 1, and both 1 1, that is SR will be 0 0 or 1 0, that is cross. So this is the excitation table for SR latch. Similarly, we can write it for D. For D, we know that D equal to next state. So next state 0 1 0 1, that will become Z. And for T, we know that it's a toggled output. So when there is no change, that is T equal to 0. 1 to 1, T equal to 0. And when there is a toggling, that is T equal to 1. So using this, we find out the one more table, that is excitation table of SR, JK, D and T flip-flop. Now what is race around condition? As we have seen in JK flip-flop that for 1 1 there is a toggling. As this toggled output again goes to the feedback and the circuit is on for entire 1, so output will again be changed. That is, the output will continue to toggle between 1 to 0 and 0 to 1. This condition is called as race around condition, and to solve this problem we use either edge triggered flip-flops or master slave circuits. We first discuss about master slave flip-flop. So what is master slave flip-flop? In master slave we use two same flip-flops and make one on at a time. That is, we use clock pulse, one directly and other inverted clock pulse. So once the clock pulse is 1, this circuit will be on and this one will be, and when the clock pulse becomes 0, this becomes off. So the output here will move towards the final output. So this circuit operates in two modes. Initially the clock pulse is 1, master SR flip-flop will be on and the output reaches to the middle stage. In this situation, slave will be off and will not pass this output to final output. Now, during the next clock pulse or when clock pulse is 0, master becomes off and slave on, and the intermediate output will reach to the final output. So this is the master slave. Similarly, this is the master slave D flip-flop and this is the master slave JK flip-flop. The final output is cross coupled with initial input, and there is a NOT gate in between two clock pulses. Now what is asynchronous flip-flop? There are two more inputs we can use, that is preset and clear. If preset is 0, output is set to preset to 1, and if clear is 0, output is preset to 1. So these two are used in asynchronous flip-flops to make these flip-flops work. So if clock is 1, clear is 1, preset is 1, then it works a normal flip-flop. When clear is 0, output is cleared, and when preset is 0, output is set. This is the operation of asynchronous flip-flop. Now we move towards conversion of flip-flop. How we convert a type of flip-flop to another? Simply, if we have to convert a flip-flop 1 to flip-flop 2, we write the characteristic table of second flip-flop and excitation table of first flip-flop, merge these two tables, find out the K-map of output terms and connect the flip-flop. So given flip-flop, then the flip-flop conversion logic which we derived from K-map and the complete circuit. For example, if we have to convert SR to D, then we write the characteristic table of D flip-flop, that is D and Qn, and based on that we find out the next state. We write all the possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. As we have known that for D, next state is equal to D. So for 0, 1, 0, 1, then next state will be 0, 1, 0, 1. Now we write the excitation for this present state and next state. We write the excitation table of SR flip-flop. So for 0 to 0, that is 0 cross, 0, 1, that is 1, 0, 1 to 0, that is 0, 1, and 1 to 1, that is cross 0. Now, using these two input D and Qn, we solve two K-map, one for S and other for R, and find out the equation, that is S equal to D and R equal to D bar. Now we connect these two equations. The given flip-flop is SR, so we make the symbol of this SR flip-flop. S is connected to D and R is connected to D bar, and this is the combined logic of SR to D flip-flop. Similarly, we can convert SR to JK by first forming the characteristic table of JK flip-flop. For input JK and present state Qn, the next state will be Qn plus 1. And then using Qn and Qn plus 1, we write the excitation table of SR flip-flop, solve the two K-map of S and R based on JK Qn inputs, and find out the equation. Draw the given flip-flop, that is SR, connect S equal to Q bar J and R equal to QK, and this is the combined circuit of JK flip-flop. So in using this type of procedure, we can convert any flip-flop. So I will make these two as the remaining exercise for you all: SR to D conversion, SR to T conversion, JK to 2 conversion, and similarly we can convert any flip-flop to another using this logic. So thank you all.